Okay, looks like it's around time for us to get started. Last day we talked more about potential energy, and really the only things we focused on was the electric potential energy around point charges. We've got one more example about that, and then we'll start a new bit of this chapter. Before we get going for today, though, does anybody have any questions about anything? No? Okay, well, as they'll come up as they come up. So we'll do another example about electric potential energy around point charges, and then hopefully we'll be good on that topic. So our example is that two protons are separated by 10 to the minus 15 meters. A third proton is slowly brought in from infinity and placed at rest at point P. For the sake of making the algebra less of a nightmare, I'm going to change this. I originally gave the height of the triangle to be that same value as D. I'm going to change it so that now we're at an equilateral triangle. So if you've downloaded the notes, make that change. It doesn't change the nature of the problem. It just makes the algebra a little bit less tangly. And I don't feel like that algebra really added much to the comprehension of the problem. Okay, so here's our new thing. This is an equilateral triangle, all 10 to the minus 15 meters. Find the change in electric potential energy of the system as the third proton is brought in. So first, the proton is all the way out at infinity. In the final situation, it's here at point P. We want to find how did the electric potential energy change. Let's do that first, and then we'll deal with part B. So initially, the proton is far away. So initial proton far away, it's at infinity. Therefore, that doesn't contribute to the electric potential energy. It's too far away to have any interactions between these two charges. Okay, so too far away, it doesn't contribute. So our initial electric potential energy is just the electric potential energy between these two charges. Just for the sake of having some symbols, let's call them Q1. It's a proton, so that charge is plus E. Call this charge Q2. That's also plus E. So our initial electric potential energy is K times Q1 times Q2 divided by the distance between them. Typically we call that R. And in our picture, we've labeled that distance D. It's 10 to the minus 15 meters. So Q1 is a proton, Q2 is a proton. This is Q times E squared. That distance we call D equals. So E is equal to 1.60 times 10 to the minus 19 coulombs. D is 10 to the minus 15 meters. K is 8.99 times 10 to the 9 newtons meters squared over coulombs squared. When we put all of this in the calculator, we get for our initial electric potential energy 2.30 times 10 to the minus 13 joules. Okay, so there's our initial electric potential energy. In our final situation, proton is at point P. Okay, so in our final situation, we've now got a third charge, Q3, that's also a proton. So now in our final situation, the total electric potential energy is the potential energy of all of them combined, all of the interactions. So these two have a potential energy, these two have a potential energy, and these two have a potential energy. To get the total potential energy, we add up all of those combinations. So UF equals K times Q1 times Q2 over R plus K times Q1 times Q3 over R plus K times Q2 times Q3 over R. This is the potential energy between 1 and 2. This is between 1 and 3. This is between 2 and 3. When we look at this equation, this simplifies really nicely for us. UF is K times E squared over D plus K times E squared over D. plus K times E squared over D. That's 3 times our initial electric potential energy. If you like numbers, we can put our numbers in there. 6.90 times 10 to the minus 13 joules. Okay, we good to here? Okay, find the change in electric potential energy. So the change is just the difference between these two. Delta U is our final potential energy, subtract our initial potential energy, 6.9 times 10 to the minus 13 joules, take away 2.30 times 10 to the minus 19 joules. Our change in electric potential energy is positive 4.60 times 10 to the minus 13 joules. Yeah?
Can you repeat how you got the initial?
The initial, so initially our proton is very far away, so there's no energy with that one because it's too far away to count. So initially all we have are these two, so the energy is the energy between those two charges. Okay, are we good to here? So what we're going to talk about, and you might like to let this just sit in your head for a few moments, is that our change in potential energy is positive. That means the potential energy increased. Kind of what does it mean about the motion that the potential energy increased? Okay, so just sort of let that simmer for a moment and we'll get to talking about that. So there's our answer to part A. Part B, what is the work done by the electric field as our proton is brought from infinity to point P? Okay, so what is the work done? So for part B, the work done by the internal forces is equal to the negative in the change in electric potential energy. And that's just a relationship between work done and change in potential energy. It comes from the definition of a conservative force. So our work done, this is the work done by the electric field. Is negative of delta U. It's negative 4.60 times 10 to the minus 13 joules. So there's our work done. It's worth thinking about that negative sign and what does that mean about for how this stuff works. So we remember that work done is positive when the force and displacement are in the same direction. Work done is negative when force and displacement are in opposite directions. So that's what work done means. So delta R, as our proton is brought from very far away to in close, the displacement is towards the triangle, but the force is repulsive because that positive charge is repelled by these charges. So delta R is toward, but the electric force is away. So it makes sense that the work is negative. Okay, so this is legitimate when we think about the physics of the situation, of what happens. There's our delta R. Okay, let's layer in one more bit, what we know about the net work done. So probably you called it the work energy theorem or the work kinetic energy theorem, a name something like that from physics 1050 or 1020, that says that the total work done is equal to the change in kinetic energy. So that probably looks familiar, hopefully. You can just review those notes if you need to. Change in kinetic energy is 1/2 m times v final squared, subtract 1/2 m times v initial squared. So let's think about this in context of our problem. The proton is brought slowly in. It started at rest, it finished at rest. So it was at infinity staying still. It's been brought in, we place it at point P, and it's staying still. Initial velocity is 0, final velocity is 0. So the net work done is equal to 0. So kind of what's going on here? This says the work is negative. This says the work is 0. So let's think about what has to happen to get that proton to this point in the triangle. So the potential energy increased, and we brought it in, and the work done by the field was negative. To go back to our analogy with gravity, if you have a car at the bottom of a hill, how do you get it to the top of the hill? You got to push it, right? So as the car goes up the hill, it goes up and gravity is down. The work done by gravity is negative, but you had to push the car to get it up the hill. Same deal here. The only way to get this proton into this triangle is for somebody to push it. Okay, so you have to do work by some external force to get that proton into place. So that's what this means. The net work is the work done by all forces. There are two forces going on here. There's work done by the electric field, and there's work done by some pushing force. And together they have to add up to be 0. Okay, so the proton was brought in by a pushing force. Oh no, my green pen is out of ink. By an external pushing force. So this force does work, the electric force does work. So the net work done is the work done by the internal force, the electric field. Plus the work done by external forces. By somebody pushing, that equals 0. So this shows us that work done by external forces is the negative of work done by internal forces if it starts and stops at rest. I would say that in general, I don't tend to stress on this stuff a lot, like on a test. Like I might ask you by the work done, but I might not ask you to get into the nitty-gritty details here. But your book does talk about it quite a bit, so if you're reading through your book, this is the sort of thing they're talking about, or if you have a different textbook. So sometimes they don't really clarify the difference between internal and external forces, but it's really good to be able to think about those things. Okay, questions? No? Okay, super. So the next slide in the notes is a homework problem, not very different from this problem. There are only so many ways you can ask the same question. So we'll get to a new topic in this chapter. So our new topic, we can't do it live in class. I'm very sorry. It's just because of the windows, so it will never work. You may or may not have done this at some point in your lives. I've done it with Girl Guide groups a whole bunch of times, and it's totally fun. So we're going to start to talk about electric potential, and a really fun demo of electric potential is sparks, little sparks or lightning, things like that. You can make this happen. You can do it anywhere. So I've got lifesavers here. It does have to be the wintergreen lifesavers. So I'm going to encourage everybody to grab a couple as you leave the room. What you have to do to see our little demo is you have to take your lifesavers and you have to go into a dark room. So like no windows if you can. For me in my house, that's like the basement bathroom. So there's no windows in there. You have to go in, you have to shut off the lights so you're in a dark room. You can do this with yourself or with a good pal. What you do is you put the lifesavers between your teeth and you have to crunch it. This is the slightly gross part. You have to crunch it with your mouth open. So you can either look in the mirror or you can have your pal look in your mouth, or you could try and take a video. The videos don't work great, but you can give it a try. What you'll see is that you actually get sparks made as you crunch the lifesavers. It's really cool. So I have a couple of bags of Lifesavers. Take a couple and give it a shot when you're home. Maybe you won't think it's as cool as I do, but I think it's pretty cool. So that's just going to be a demo. If I can get the Van de Graaff working, I'll bring that in and we'll do a bigger demo here in class, but this is a little one that you can do at home. Okay, so that's going to be our example. Let's start getting into what we're talking about. So this slide is a review of what we talked about as we developed electric force and electric field. So we drew analogies between gravity and electromagnetism. We said that if we have a mass m in a gravitational field g, it will feel a gravitational force equal to the weight m times g. And we defined our gravitational field as the gravitational force per unit mass. So we talked about those things with gravity. And then we said if we have a charge Q in an electric field, it will feel an electric force. And we defined our electric field as the electric force per unit charge. So those were things we talked about with electric fields and gravitational fields. Both of these things are vectors. That's really important, so I'm going to write that on the side. So what we said, what we could take away here, is if we place an object in a field, it will feel a force. We've just spent a couple of classes talking about energy. So if field is force per unit charge, what is energy per unit charge? So a field tells us what the force is. What tells us what the energy is? So that's where we're going to go next. So this idea gave us force and field. Next, we're going to talk about energy. So I pre-typed up some notes on the next slide. So now we'll come down to our next bit. Our top two here, as a reminder, are vectors. And we really well established the relationship between electric force and electric field. Now we're asking what determines energy. So field is force per unit charge. What is energy per unit charge? So let's remind ourselves what the energy is. Gravitational potential energy was UG equals m times g times y. Our electric potential energy, UE, was charge times E times S. Okay, so that's what we've been working on. This was the electric potential energy of charge Q in an electric field E at a distance S from the negative plate. Okay, so that was our expression right here. These are energies that had units of joules. So now, field is force per unit charge. We're going to ask about energy. What is energy per unit charge? What is U over Q? So energy per unit charge, UE over Q. So I divide by Q on both sides. We get E times S. This is something new, and we call this potential. You probably know about, maybe you called it voltage in high school. This is the same thing. So our potential has a symbol of V. It has units of volts. And the symbol for that is also a V. And electric potential, or potential V, is the electric potential energy per unit charge. So what that means is if a charge Q is in an area with potential V, it's going to have electric potential energy U. Okay, so that's what this is telling us. This boils down to potential energy is equal to, potential energy is equal to Q times V. Okay, so U over Q is V, or U is Q times V. You can and do the same thing in gravity. So gravitational potential energy divided by m gives us G times Y. You can do some calculation and see that it's equal to this. You probably wouldn't see this expression in a standard physics degree, but if you studied astronomy, you would do a lot with it. So gravitational potential is a thing, but it's something that the astronomers use. Okay, so some notes about potential. First of all, potential energy is a scalar, and if we divide our potential energy by a charge Q, that's also a scalar. So we're going to have to start being really careful between our vectors and our scalars so we don't get those confused. Potential V has a lot of different names. So it's called potential difference, it's called electric potential, it's called electric potential difference, and it's also called voltage. For what it's worth, I will most often say potential or potential difference. Those are the terms I tend to use. But you might see any of those words in any of the different books you look at or any of the people you talk to. And what else? A volt, since potential is energy divided by charge, a volt is the same thing as a joule divided by a coulomb. Okay, so our field is force per unit charge. Our potential is energy per unit charge. Are we good to there? So there's our definition of electric potential. If our field is constant, then our potential is E times distance. So we're going to come back and spend some time there. But first we're going to look at the potential due to point charges. So we'll do more about that first before we come back to the constant fields. So we had a slide like this when we found electric field around a source charge. We're going to go back to that same idea, and we're going to find the expression for the electric potential around a source charge. So we've got a point charge Q, that's our charge down here. And this point charge Q is our source charge. Back in our electric fields chapter, we said that this charge makes an electric field, which is absolutely true. Now we're seeing is that there's also an electric potential associated with it. So we've got our source charge Q right here. We'd like to find the electric field at some point P. So we'll label P on our diagram. Really important here is P is just a point in space. There is nothing at point P. Okay, so the only charge we have here is our source charge Q. Nothing at point P so far. And I'm going to say that our point P is a distance R from our charge Q. So now the next thing we're going to do is we're going to take a test charge Q primed and we're going to place it at point P. And this is just like what we did with our electric fields. With electric fields, we put a test charge there and we calculated the force. This time we're going to put a test charge here, Q primed, and we're going to ask what is the energy. So last time we asked about force, this time we ask about energy. So we're still a distance R away. This is our charge Q. And what we know is that if we have 2 point charges, the electric potential energy between them is K times the first charge times the second charge divided by the distance between them. And this might be a decent place just to remind ourselves that we include the signs of charges. Or electric potential energy is allowed to be positive or negative. Okay, are we good to hear? So this is how we find the electric potential energy when we have 2 charges together. Now we know that our electric potential is our energy per unit charge. So we'll take away our charge and ask what's left over, what's left behind. So now we just have our point P. Our electric potential is our electric potential energy divided by the charge. So that's equal to KQ over RQ Q times Q prime divided by R divided by Q prime. Our electric potential is K times Q over R. So there's an expression for the electric potential at a distance R from a point charge Q. So there is an electric potential associated with a source charge, and that electric potential is what gives us the electric potential energy. We talked about the fact that if two charges are really far apart, then our R becomes approximately infinity, and our energy becomes approximately 0. If two charges are really far apart, there's no interaction. So we talked about if R is really big, so R approaches infinity, our electric potential energy is about 0, which meant no interaction. We now see that that means our electric potential is also about 0. Okay, so at a very far distance from every charge, there is no electric potential once we're far away. So often you might see V equals 0 at R equals infinity is the reference point. Feels kind of like the statement of the obvious, but there we go. Physics often likes to state the obvious. Okay, we good to hear? Yep.
So the potential energy isn't dependent on if we change the point charge. Like if we had a much larger point charge, it wouldn't have a different potential energy or different potential energy.
Let's see. If you change either of these charges, you will change the potential energy because the energy depends on both these charges. If you change this charge, the source charge, you'll change V. If you change this one, you won't change V. Yeah. So the potential depends on this charge only. The potential energy depends on both of them. Okay, so there's our electric potential around a point charge. This feels like a very good time for this slide. So I mentioned this a little while ago that we had 4 quantities, and now we see that all those equations look an awful lot alike. We have electric force and electric field. These two are vectors. With our force and our field, they go as 1 over r squared. Okay. With our potential energy and our potential, those are scalars, and they go as 1 over r. The force and the energy, they're interactions. The field and the potential, those are properties of the source charge. So 4 equations that all look an awful lot alike, but they're different things. So make sure you don't get them confused. If I was, making a sheet of notes, I would certainly have these words next to these equations so I didn't get confused on a test. We know a lot about the relationship between these two. So the force is the charge times the field. We know about the relationship between these two. Force is the change in potential energy with respect to distance. We know about the relationship between these two. Energy is charge times potential. Hopefully by the end of today's class, we're going to get to the relationship between these two, field and potential. Okay, so hopefully we're going to get to here by the end of today's class. But first, we're just going to do some examples, all about potential around point charges. So let's start straightforward. And the first thing is my diagram cut off the distance. Our distance here, between here and here, is 0.750 centimeters. Okay, so yours probably got cut off too if you downloaded the notes. We take a 1 microcoulomb charge, we place it at the energy. So this is gonna be our source charge, this is Q1. And let's ask some questions and do some calculations. First of all, what is the electric potential at points A and B? Okay, so this one is going to be straightforward. This is just going to be KQ over R at point A and at point B. You might notice here that when we were doing this with electric fields, and we did these examples with electric fields, we always had to draw those vectors, right? And we had to find the components. This time it's different because potential is a scalar. We're not drawing vectors anymore because we don't have a direction. So our potential at point A, my potential at point A is K times my source charge divided by the distance between the source charge and point A. I'm going to label that as R with an A on it. And then I'm going to show that distance in my diagram. So from here to here is RA. Put my numbers in, 8.99 times 10 to the 9 newtons meters squared over coulombs squared. Q1 was 1 microcoulomb, so 1 times 10 to the minus 6 coulombs, divided by RA, 0.75 times 10 to the minus 2 meters, gives us a potential of 1.199 times 10 to the 6 volts. I'll write the word scalar here just to remind us that we don't need any direction because it's a scalar, it doesn't have a direction. So there's my potential at point A. I'm also asked for the potential at point B. My potential at point B is going to be VB equals K times Q1 divided by the distance between point B and charge 1. So on my picture, that's from here to here. I notice that this is a hypotenuse of a right angle triangle. I can use Pythagorean theorem to find my distance RB. So that's going to be the square root of 0.75 centimeters squared plus 0.75 centimeters squared equals 1.061 centimeters. So there's my RB. 8.99 times 10 to the 9 newtons meters squared over coulombs squared times my Q1, 1 times 10 to the minus 6 coulombs, divided by 1.061 times 10 to the minus 2 meters, gives us a potential at point B, 8.48 times 10 to the 5 volts. If you look at your potential B, you see that it's smaller than your potential A, and that makes sense because it's further away, right? Potential goes as 1 over R. If you're further away, you have a smaller potential. Part B, what is the change in electric potential energy of a 2 nanocoulomb charge moving from point A to point B? So part B now, we have a new situation. I'm introducing a new charge. I'm going to call this Q2. And this is moving from point A to point B. So this is what's happening in my part B. If we think about what's happening, we have a charge. It's in an area with potential, so we know it's going to feel electric potential energy. We're asked for the change in electric potential energy. So delta U is going to be the final potential energy, that's at B, subtract the initial potential energy, that's at A. If you were still in your mindset of the things we did before potential, you might do K, Q1, Q2 over RB, subtract K, Q1, Q2 over RA. That calculation would work, you'd get the same answer, but we're going to use it in terms of potential because we're doing a potential example. So my potential energy at point B is my charge 2 times my potential at point B. So this is the electric potential energy of charge 2 at an area with potential V. Okay, so that's what that statement is. Subtract my electric potential energy of charge 2 at point A. So that's Q2 outside of VB minus VA. So an equation that's often written on a formula sheet is delta U equals Q delta V. Okay, so this is the long way of getting to that equation. Oh my goodness, sorry, I forgot I zoomed in. Delta U is Q delta V. Okay, same thing here, and that's often the one that's given on a formula sheet. So let's put our numbers in. Delta U is my charge Q2, 2 nanocoulombs. VB was 8.48 times 10 to the 5 volts. Subtract 1.199 times 10 to the 6 volts. That change in electric potential energy as my charge moved from point A to point B was negative 7.03 times 10 to the minus 4 joules. It's moving to a place of lower potential energy because it's getting further away from the charge. So lower potential energy once it's further away. So it makes sense that our delta U is negative. Okay, good to hear. And then how much work is done by the electric field as the charge moved from point A to B. So our work done, part C, by the electric field is minus delta U equals plus 7.03 times 10 to the minus 4 joules. Work is minus delta U. So the charge ultimately is moving away. The force is away because it's repulsive. So our work done is positive. So the signs make sense here. Okay, questions? All right. So that's electric potential around one charge. When we did electric potential energy, we looked at what happens with a bunch of charges. We'll do the same thing with our electric potential. So how do we find the electric potential if we have more than 1 point charges? So in this picture, we have 3 charges, 3 source charges, and we want to know what is the potential at point P. Three source charges. Again, if this were an electric field problem, you would be drawing your vectors at point P, you'd be finding the components, you'd be adding the x's, adding the y's to get your net field. Electric potential is a scalar, so there's no drawing arrows here because it's not a vector. So my net potential at point P, I've got a potential due to 1, due to 2, and due to 3. My total potential is just those 3 things added up. So to get your total potential, you add up each of the individual potentials. My potential 1 is K times Q1 over the distance between charge 1 and our point P. I'll call that R1. And then likewise for V2, that's K Q2 over R2. And ditto for V3, K Q3 over R3. Okay, KQ over R for each of them, add them all up, and you're done. So your general expression for I charges, your net potential at point P would be the sum of K times each charge divided by each distance. remembering that potential can be positive or negative. Okay, so we're including the sign of charge here. This is a scalar. And our potential is a property of the source charges. Okay, so this potential is made by our set of source charges. Now, if we take a new charge and put it at point P, we know that charge will have a potential energy, and we can find what that potential energy is. So if we take a charge Q0 and place it at point P, it's going to have a total electric potential energy UE is the charge that's placed there times the potential it's sitting in. So this is how we deal with more than one charge. These problems are like what we did with our electric fields. You can find the net field. Then if you put a charge there, you find the force doing Q times E. This one, we can find the net potential. We put a charge here, we can find the energy by doing Q times E. So similar format to the problems, you just remember which are vectors and which are scalars. Okay, questions? Okay, so we'll go through an example next. So we're going to build on that example we did a few moments ago. We've got a 1 microcoulomb charge placed at the origin. I'm going to call that one Q1. And a 2 microcoulomb charge is placed at 0.75 meters on the x-axis. I'm going to call that charge Q2. These are the source charges. And then we're going to ask the same questions. What's the potential at point A and B? What's the change in potential energy if we move a charge from here to here, and what was the work done by the field? So we'll repeat our problem, but now we have 2 source charges instead of just 1. So for part A, what is the potential at point A and what is the potential at point B? So my potential at point A is going to be the potential at A due to 1 plus the potential at A due to 2. So those two things added up. My potential at A due to 1 is K times Q1 divided by R, let's see, A1. Just try and get my notation there a little bit clearer so we don't make a mess of things. So A1, RA1 is the distance between charge 1 and A. That's 0.75 centimeters. So VA1 KQ1 over RA1. K times 1 microcoulomb divided by 0.0075 meters. So that potential is 1.199 times 10 to the 6 volts. So we did that in our last example. Our potential at point A due to charge 2 is K times Q2 over R to point A between point A and charge 2. So that's this distance. Okay, I'm going to try and keep my diagram neat. So this is the hypotenuse of our right angle triangle. We did that equation last time. 0.75 squared plus 0.75 squared gave us 1.06 centimeters for the length of our hypotenuse. So the potential at point A due to charge 2 is K times Q2 times R of A2. Charge 2 was 2 microcoulombs, so 2 times 10 to the minus 6 coulombs divided by 0.0106 meters. That potential is 1.695 times 10 to the 6 volts. Okay, so those are the two ingredients. Add them together to get the total potential is 2.894 times 10 to the 6 volts. Everybody okay with the potential at point A? Okay, we'll do the same thing and we'll find the potential at point B. Okay, so both of our charges are making potential. We found the total potential at A. You can also find the total potential at B using the same method. So my potential at B is the potential at B due to charge 1 plus the potential at B due to charge 2. K times Q1 divided by the distance between charge 1 and point B. So that's from here to here. Again, we've got the diagonal of our square here. R between B and 1 is 1.06 centimeters. So we can go ahead and do that calculation. So that potential is equal to 8.476 times 10 to the 5 volts, plus the potential at point B due to charge 2, which is K times Q2, divided by the distance between point B and charge 2. From here to here, that's our 0.75 centimeters. So VB2 is K times charge 2 divided by the distance between B and charge 2. K times 2 times 10 to the minus 6 coulombs divided by 0.0075 meters. The potential at point B due to charge 2 is 2.397 times 10 to the 6 volts. Add those two guys up, you get the total potential at B, 3.245 times 10 to the 6 volts. Okay, any questions here? So this is the same as what we did in our last example, except now we have to include a second charge. All right, part B, what is the change in electric potential energy as we move a charge from point A to point B? So there's our charge Q3. We're going to move it from A to B. I'm going to try and finish, but I don't want to keep you over time. So I'm not going to do that lengthy derivation where I found that delta U was Q delta V. So part B, delta U is Q3 times delta V. So this was the result we got from last time. Q3 VB minus VA. Q3 was the third charge we put in there, that was 2 nanocoulombs. So that gives us a change in electric potential energy of 7.02 times 10 to the minus 4 joules. So when we moved our charge, we moved it to a place with higher potential, so it got a higher potential energy, so delta U was positive. We moved it closer to a bigger charge, essentially. Our work done was the question for part C, that's minus delta U, so minus 7.02 times 10 to the minus 4 joules. Because we've taken this positive charge and we've pushed it closer to a bigger positive charge, we had to do some external work to get that there. The work done by the electric field was negative because we pushed it in, but the electric force repelled it away. Okay. So that takes us up to the end of our time. Yeah, so we'll keep going Friday. Yep.
Is there a reason that the extra electron, or the extra charge, is negligible in the change in force compared to the two? Because the last one was 7.02 and 10 was -4.
Yeah.
This one's 7.04 or 7.02 times 10 to the -4. Even though we added a whole other electron, is there just a reason that it's a negligible versus the change in force?
No, I think it's just more of a fluke for how it turned out. Yeah. No.